recording. Okay, so we were going through this example, and we have calculated the values of the derivative using the forward and the backward and the central difference methods. And I'll just look at the values here. These are the values that we calculated. Now, if we look at the true relative errors, so in the forward difference, we have 58.9%, 39.7%, 9.6% errors. So we can see that these are big errors, and here we have something like 10% error. Now, once we change the step size and make it 0.25, then we find these values for the derivatives, and the true relative errors is found as 26.5%, 21.7%, and 2.4%. Now, if you compare them to the previous values, you can see 58.9 and 26.5. So let's say almost 60, almost 40, almost 10. Now, once we make the step size half, we expect the true error, not the relative error, the true error to become half, but it also reflects on the true relative error. We see that it has also become almost half. From 40%, let's say, it has reduced to almost 21%. Now, the center difference is not of the order of h like these two. It's the order of the h square. So h square means that if you decrease the step and you made it half of the previous one, then the error will become 0.25. So it means quarter of the previous one. So we can see that we had almost 10% error. It has become almost, let's say, 2.5. So it has not decreased and become 5%, but it has decreased by 4 times. So that's the meaning of having an error of order of h square. It means that it is going to be decreasing by the square of the step size. Now, if your step size was, let's say, 0.1 of the previous step size, then squaring it will give you 0.01. So that it means that if you decrease your step size by 10, your error is going to decrease by 100. So that's the meaning of having order of h square in the error. The total numerical error that we have in any calculation then or any computation is the sum of the truncation error and the round off error. The truncation error generally increases as the step size increases, as we have seen here. That's either of the order of h or h square or whatever power of h. If we increase the step size, the error is going to increase. So we can see here the truncation error. As the step size increases, truncation error increases, while the round off error decreases as the step size increases. So as we increase the step size, the round off error decreases. Yeah, because if you have numbers close together, let's say if you have 0.3 and then you take 0.30001, then the difference between them might be rounded off to 0. So you'll have a round off error. But if you have 0.3 and 0.3 0.6, let's say, then the difference is going to be 0.3. You don't expect to have round of error in that case. So usually the round of error decreases when the step size increases. So you have something increasing, something decreasing. The total summation then will be somewhere in the middle. So you cannot just take a general rule and say that I'm going to decrease my step size and get a smaller error. You have to rely on something in between so that the total error at the end remains somewhere not so high, not so low. Of course, you can't go low because that's a total summation of the errors. For most of the engineering application, there is no exact solution, means no analytical solution. We must settle for some estimate of the error in our calculations. Generally, we don't have any systematic approach to find errors. Different techniques have different ways of how to deal with the errors. But we have to have some sort of an idea about the error that we end up with when we use the numerical techniques. Taylor series is going to be our primary tool for analyzing both the truncation and the round of errors. And always remember, when you work with numerical computations, there is no such thing as 100% exact or 100% correct when you deal with numerical error, numerical analysis or numerical solutions. You have to analyze each solution by considering the error estimates that you could end up with using that method. Other errors that could end up in a numerical solution, blunders, are errors caused by malfunctions of the computer or human imperfection, something that's let's say human errors. Model errors, the errors resulting from incomplete mathematical models. You try to bring in so much simplification to the model that it's not really well defining your physical system. Data uncertainty, that the data that you are using in your model, let's say the physical properties that you are using or whatever data you have that you use, let's say for temperature or pressure or whatever other properties, that itself is not reliable. So, and of course that's going to end up causing errors in your solutions. So with this we finish chapter 4. We'll go to the book and take some problem from there. I'll start first with the question 4.8, just to see what we mean by errors. Sometimes this thing doesn't get copied. The question says the derivative of the function 1 over 1 minus 3x square is given by 6x over 1 minus 3x square, the whole square. Do you expect to have difficulties evaluating this function at x equal to 0.577? And he says try using a 3 and 4 digit arithmetic with chopping. Now chopping is what computers do. Instead of rounding off, computers chop off numbers. So let's say if you are using 3 digit chopping off, then 3.012999. If you are let's say rounding it off to 3 decimal places, it just comes and chops off these numbers. It's not going to make it 3.013. No, it keeps it as 3.012, just cuts off these numbers. So let us see now what we get when we try to use this 3 and 4 digit arithmetic with our calculation here when x is 0.577. Now let's find the true value. Of course, we are looking at this function, which is a derivative, not the actual function. I'll just put this in calculator and find the answer. I forgot the square. So the answer is 2.3529 10 to the power 6. So that's the actual value. Now let's start now and see what happens if you use three-digit chopping. Now our function is 6x, so I'll find 6x means 6 into 0.577. So 6 into 0.577. It comes out to be 3.4620. Now, after chopping off, after three digits, this is chopped off, and we are left with 3.46. Then in the denominator, we have 1 minus 3x square, the whole square. So I'll find x square, which is 0.577 square. So 0.577 square, 0.3329 2929. So again, chopping after three digits, and we'll be left with 0.332. Then it is multiplied by 3, so we have 3x square. So we get 3 multiplied by 0.332. This is an easy one. 699. So we get 0.996. Then we have 1 minus 3x square. So 1 minus 3x square is 1 minus 0.996. Zero 0.004. And then what we have, we have 0.004. In the denominator, we have 1 minus 3x squared, the whole square. So 0.04. So we'll have 0.00016. Okay. Then we have the final calculation, which is 6x will be 3.46 over 0.00016. It comes out to be 21625.0. After 3-digit chopping, it will become 216000. So that's the answer that we get using 3-digit chopping. Now I'll just find the error in this value. Is the true value. We found it to be 2.3529 minus the approximate value divided by the true value multiplied by the 100%. Let me find absolute value of the true value minus 216000 divided by the true value multiplied by. That's 90.82% error. You see what we get? The number was 2.3 million. What we ended up is only 216,000. Is 0.2 million. So using the rounding off, not the rounding off, using a chopping by 3-digit arithmetic, the number, instead of becoming 2.3 million, has become only 0.2 million. We have 90.8% error. So what we got is not even 10% of the actual value. Now we repeat the same thing, but using 4-digit chopping. I'll put it here so that I can see the calculations we have done before. So 6x is 6 multiplied by 0.577 is 3.462. So we take all the 4 values. X square is 0.577 square, which was 0.332929. So we took it before as 0.332. Now we add one more digit. 3 times x square will be 3 multiplied by 0.3329. It becomes 0.9987. 1 minus 3x square, 1 minus 0.9987, (0.0013). 1 minus 3x square, the whole square, 0.0013 square. I'll just write it as 1.69 into 10 powers minus 6. This is what I got. But you can see we have only three significant figures, so we don't have 4 significant figures anyway. You can put one extra 0, make it 4. It doesn't matter. Then we do the final calculation, which is 6x over 1 minus 3x square, the whole square, which is 3.462. So 3.462. We get 2.048 10 to the power 6. We can look at the error, the true value, which is 2.3529 10 to the power 6 minus 2.048 10 to the power 6. And we get 12.96% error. So it's not so bad as the previous one, where we got only 0.2 million. We got 2 point something million, but it's not 2.35 million. So using even 4 digits, we ended up with a 12.9% error. So this is how the round of errors come into play, and you end up getting wrong answers because of the numbers of digits that have been used in the calculations. So that's problem 4.8. I want you to do 4.9 by yourself, please, quickly. Find this value. Let me copy it for you. We'll only do part A. You can start working, please. Are you working on it? Okay. I'll give you 7 minutes for it. I don't know. Let us see what others find. It doesn't matter. There is no angle involved here. So radians, degrees, it is all same. Okay, let us do it together now. The equation is x cube minus 7x square plus 8x minus 0.35. Just let me check. X cube minus 7x square plus 8x minus 0.35, and x is 1.37. Okay, I'll start with the first one. I'll find 1.37 cube. Anyone found this 1.37 cube? What did you find it as? 2.57. Okay, so that's 2.57. X square 1.37 square. One point 87. 7 times this, 13.0. I'll just mark the numbers that we need. We need this. We need this. 8 times x, 10.9, right? And minus 0.35. So we have 2.57 minus 13.0 plus 10.9 minus 0.35. 2.57 plus minus 13 plus 10.9 minus 0.12. So that's the answer that we get is 0.13. The true value, anyone found the true value? 1.37 q minus 7 3. 0.4 0.04353. So you can find the error is the true value minus the approximated value. The approximated value is 0.12 divided by the true value. So it is 178.7%. How did you find it out as 0.5% and 50%? Yeah, so that's the right answer is 178.7%. Okay, we don't how true value minus this. This is the true value minus 0.12 divided by the true value multiplied by 100%. Okay, we don't have much time. I'll go to fold 10. Oh no, fold 10. Go to 411. It says the Maclaurin series for cosine x is given by this equation. Starting with the simplest version of cosine x equal to 1, add terms one at a time to estimate cosine pi by 3. After each new term is added, compute the true and approximate percent relative errors. Use your calculator or MATLAB to determine the true value. Add terms until the absolute value of the approximate error. Estimate falls below an error criterion conforming to two significant figures. Now, let me copy this part first. Okay, so that's the problem. We want to find cosine of pi by 3 and then keep adding terms one by one. So we'll make a table like n and then the approximate value. Oh, sorry. Okay, so far I was just copying the problem. That's problem 411. We'll make a table. We'll put the number of terms, find the approximate value, and then we'll find the approximate error and the true error as he wants us to find in each term. Now, when we start with the simplest version, cosine x is equal to 1. That is when you take only one term and you say cosine x is equal to 1. You stop at the first term. The true value of cosine pi by 3 is 0.5. So the approximate error, because we don't have any other value to compare with, there is no approximate error. The true error in the first one is true value minus approximate value divided by true value into 100. So that is 100% error. So 100%. Now when n is 2, we'll include two terms. So this will be 1 minus x is pi by 3 square divided by 2. So 1 minus pi by 3 square divided by 2. This pi by 3 square divided by 2. It comes out to be 0.4517. Now you can find the approximate error, which will be this value minus the old value divided by the new value. So 0.4517 minus 1. So it is 121% error. The true error, of course, between 0.4517 and 0.5. So 0.5 minus 0.4517 divided by 0.5. So we get a 9.66% error. Now, when do we stop? Of course, you keep adding terms and find the values. He says stop at an error conforming to two significant figures. We have seen the stopping criteria. It says 0.5 into 10 to the power. What was it? 2 minus n? I think so. We'll go up and find it. 0.5 in 10 to the power 2 minus n. So now it is two significant figures, so it will be 0.5 10 to the power 2 minus 2. 2 minus 2 is 0, so it is 0.5%. Of course, you always compare this with your approximate error. So far it was 121%. You have to continue until the error falls below 0.5%. So you keep adding terms 3, 4, 5. See when you are going to get the error less than 0.5%, and you can stop there. It's just a matter of repeating the steps. Please do try it yourself, and you can try other problems. I'll stop here. If you have any questions, please feel free to ask. Stop recording.